instead of talking about like kind of the theory of quantum computing in general and why it's supposed to be so wonderful and stuff like that, I'm going to come at this from the angle of a trained experimental physicist and tell you about the kinds of computing problems that I see more at the lower end of the stack per se. So I'm not really going to talk about applications except for maybe one of them that was some recent work that I actually did with a theory group at Pittsburgh, and because it has to relate with how we understand mapping real life quantum problems onto an actual quantum hardware, which is kind of a big problem. So first I'll start with a little overview, and I'm going to come at it with a different angle as well. So most people recognize that the first time that anyone talked about quantum computers was Richard Feynman, who's in here the back row of the first Physics of Computation conference, which was jointly hosted by MIT and IBM. There are IBMers here, such as Rolf Landauer, who's sitting on the front row just slightly to the left, if you can see my mouse, and Charlie Bennett, who's taking the picture, and he's still with us today. I have lunch with him sometimes. So the reason why Richard Feynman wanted a quantum computer is because he knew he had these quantum mechanical problems that he wanted to solve, and I'm going to touch on that a little bit later. But mainly, there's this other kinds of research that IBM was doing back in the day, and that was understanding the physics of computation. Now, computer scientists, to their credit, took the idea that you could do computing on anything beta Boolean logic, and you can abstract away the mathematics and build, a capability to solve incredible mathematical problems. But what Rolf Landauer and Charlie Bennett were doing at IBM was trying to study the fundamental energy costs of computation, i.e., is there a minimal cost of doing a computation? There, it turns out there is. It's the von Neumann-Landauer limit. I think that's right. And they were also considering what if you use quantum computing, because quantum computing is inherently reversible until you deal with dissipation. And so you could feasibly do computation without any energy cost. And that was because just like today, IBM was building huge computers in the 70s that took up a lot of energy, just like people are mining Bitcoin right now and putting all their applications on the cloud. So it had different applications, but people kind of came to quantum computing in much a similar way. And so you can start thinking about, well, what is my, skipped over a slide. Okay, well, I'll just tell you what it is. I just had some pictures, but basically you can think of classical computer as anything that stores classical information, such as the 0 or 1 of a light switch, whether current is flowing or not flowing through a transistor, or the direction of the polarity of little magnets in your hard disk drive. So you can think of anything as 0, 1, and they're very, very nonlinear. They have a latching behavior associated with them. So you don't have this kind of like analog type situation where you have continuous operations like you do in quantum computing. Now, if instead you took 0 and 1 and you wanted to encode it in a quantum system, well, you could do that by saying the state that represents the ground state of an atom is a 0, and the state that represents the 1 state of an atom, or excited state of an atom, represents a 1. And you could also do these things with spin up or spin down of electrons, or as we'll see later, the oscillations in tiny superconducting circuits that we use. And the thing about that is that if you're representing those states by those quantum systems, you're essentially representing a wave function for that 0 and for that 1. And because that wave function obeys Schrodinger's equation, which is a linear differential equation, any superposition or essentially linear combination of those two solutions is also a solution, which means we can actually have this much larger area of information, because you have this kind of continuous thing where you represent on a block sphere, which I have on a later slide. So we'll go through it then. And the other thing you can do with qubits is you can entangle them with each other, and that's because you can put them in a state where neither of them is represented by an individual wave function, but a combined wave function, and it's impossible to describe either of those locally. So I'm going to kind of tell you how we do those with superconducting circuits. And so what does this look like? Well, IBM essentially leveraged all its ability in classical computing and applied the same thing to fabricating planar systems, where instead of using semiconductors, here we're using superconductors. Now, these are on silicon as well, but instead what we're doing, instead of treating the silicon as a semiconductor, we're actually just treating it as a substrate, maybe with some certain dielectric properties, where we sputter deposit a superconductor. In this case, all the features you can see is a normal metal, or sorry, an elemental metal niobium, which happens to become a superconductor when you cool it down to below 9 Kelvin, which is 9 degrees Celsius above absolute 0. So the main feature of this is a 5-qubit chip, and this is the first type of quantum, or this is representative of the first quantum computer that IBM put on the cloud in 2016, so almost 5 years ago. These 5 qubits are inside of each one of these pockets. And if you look inside those pockets, you'll see this equal sign that's rotated by 90 degrees. Those equal signs, those 2 pads, represent the pads of a capacitor. That's all it really is. It's a capacitor made out of superconductor, so it's lossless. The other part inside of it is something we call a Josephson junction, which is a break in a superconductor. So in this case, we form aluminum as our superconductor, which becomes superconducting below 1 Kelvin. And then we let it oxidize to form an insulating barrier. And then we deposit aluminum back on top of it. And in this way, we get this Josephson junction or constriction. And what that electrically does is it serves as a nonlinear inductor. So then we have something that looks like an LC oscillator. And so this is very important because the other parts of these things are oscillators as well. These squiggly lines you see right here are superconducting microwave resonators, a special kind we call coplanar waveguide, but it's essentially if you took a coax cable like you had at home for your cable TV and you flattened it onto a chip, it would look like that with the signal pin in the middle and ground planes on the side. We use these to do a number of things, such as connect to the external environment, which allows us to put signals to control the qubit, and it also aids in measuring the readout state of the qubits. They act as filters at the qubit frequency because the frequency of these resonators is detuned from that of the qubits, which means it kind of suppresses spontaneous radiation. And then they also will combine the qubits so that we can perform operations to entangle them. And we'll go through some of those later as well. Now, what the main difference between these 2 different kinds of oscillators are is this microwave resonator here is just going to be an LC oscillator, a linear LC oscillator, if you took a circuits class, or if you took a quantum mechanics class, you might call it a harmonic oscillator. Unlike our nonlinear LC oscillator up here, because we have a Josephson junction as the inductive element instead. And that will give us an anharmonic oscillator. And the main difference here is that, well, if you want to encode a qubit in one of these systems, you might say, well, I can make 0 the ground state, and I can make 1 the first excited state, and then I can just keep myself in that subspace. Well, it turns out if you have evenly level spaced energy profile, if you try to drive transitions from 0 to 1, you're going to drive them from 1 and 2 as well, because they're all equally spaced in energy. So the key Josephson junction element comes in here in order to make this oscillator anharmonic, so that the energy difference between the 0 and 1 level is different from that in the 1 and 2 level, usually to the tune of about 300 megahertz difference. So our typical 0 to 1 transition frequency is 5 gigahertz, which means the next one's going to be like 4.7 gigahertz. And if we take that temperature and we multiply it by Boltzmann's constant, we multiply it by, or take that frequency, multiply it by Planck's constant, divide by Boltzmann's constant, we see that that energy level corresponds to 240 millikelvin, which means not do only we need to keep this at an extremely low temperature at which metals become superconductors, but also at an energy level much less than 240 millikelvins, because you want to be able to isolate and keep those energy levels from becoming too broad, because that will introduce errors in your quantum computations. Okay, so that's kind of an overview of what we're looking at. So let's come back to the block sphere, which is what I didn't have before. So basically what we do is we represent our computational states on the sphere, where 0 is the North Pole and 1 is the South Pole. And then any state on there is a superposition with some coefficients alpha and beta, which can be in general complex. It's normalized to 1, so it's on the surface of the sphere, but I like to think of it as the surface of the Earth. And quantum mechanically, if you're at the equator, you're like in a 50% 0 state and in addition to a 50% 1 state. And then whenever you perform a measurement on that, even if you're in a definite state, like right there at the x-axis, your measurement is going to be probabilistic, and you'll collapse to a 0 50% of the time and a 1 50% of the time. So you can essentially manipulate these quantum states as if they were definite states, but your measurement result is going to become probabilistic. So this is always something to keep in mind when designing algorithms. But basically, this is just linear algebra, where we physicists use this thing called Dirac notation because we're lazy, where the 0 here with the pointy bracket represents the column vector 1, 0, and 1 here with a pointy bracket corresponds to 0, 1. And then we have special matrices that describe the measurement and motion of these, and we call them the Pauli matrices. These were originally figured out by Wolfgang Pauli to describe spins in quantum mechanics, but they're very closely related to the quaternions. So basically, these represent the measurement axis you would measure to find the eigenstates of each of these operators. In particular, we only measure along the z-axis in our superconducting qubits. So you can see that the state 0, 1, 0 here is an eigenstate of this z operator with eigenvalue 1. And this 1 state here, 0, 1, is an eigenstate of this z operator with an eigenvalue -1. But these aren't just useful for measurement. In fact, quantum mechanically, they generate rotation. So this is something you might have seen if you've taken the quantum mechanics class. But basically, we just get a unitary matrix. All the matrices that describe movements of qubits are going to be represented by some sort of special unitary group. And you can rotate around any normal axis n by an amount theta by essentially exponentiating this this matrix, which is, or this vector, which is a dot product of that normal unit vector with a vector of polymatrices. But then you can write it down in like a nice little form right here, where you have the identity matrix times cosine theta minus 2 minus the contribution times sine theta minus 2. But if you actually like write it out, it gives you a really easy way to do the math. So for example, a unitary that represents an x rotation of an angle of phi is going to be given by this matrix right here. And this kind of shows you how you can just use linear algebra to understand what the operation of the quantum circuits is, which I think is a very mathematically useful tool. And I always like to compare it to the physics of what's going on in the system, because they're, of course, related, and all your errors are going to come, or a lot of your errors are going to come about because the physics is not obeying the unitary matrix you imagined it to be. So physically, what do we do for single qubit control, like we just described? We're going to hit the qubit with microwave photons. So these microwave photons are typically shaped similar to a Gaussian, which I'll show you a little bit more later. And they just consist of a carrier frequency at the qubit transition frequency. So that 0-1 transition frequency is going to be about 5 gigahertz. And what this is going to do for you is this will give you a rotation in any axis of the XY plane of the Bloch sphere. So the only difference is you can change the phase of that carrier frequency, and that will change the axis of rotation. So for example, a rotation around the x-axis is just a 90-degree phase shift around the rotation of the y-axis. And this is kind of a trick we can use to decompose things and understand them, because what we actually do for z rotations is you can just combine x and y rotations, except you might understand that there's always going to be error associated with this because they take a finite time. So there's going to be decoherence. There's always going to be some more errors, which I'll talk about later. So we actually use our z rotations by a trick by taking them into account during the compilation of the circuit. We recognized only a few years ago that z rotations effectively just change the phase of all the subsequent circuits after it. So this is actually compiled down in hardware. It's something we call a frame change, where we just change the phase of the subsequent circuits. And so we don't actually do any z rotations. We just take care of it in compilation. And in that way, we can essentially get a lower overall single qubit average error. And so that's a little compilation trick right there. And we're kind of full of all of these. So another thing I'd like to bring back to classical computing is you can understand a universal quantum computer just as you can understand a universal classical computer. So for a universal classical computer, I'm sure you all took the computer science department. I remember taking my digital logic class, and you understand from that there's one of two 2-to-1 or one of two gates you can choose to be the formation of your universal quantum computer, and that's the not and the not or, which just inverts the AND gate, like 0 and 0 is equal to 0, which not that is 1, 0 and 1 is 0, not that is 1, 1 and 1 is 1, not that is 0, and vice versa for the NOR. So you can build a classical computer with this and like any ancilla. And that will represent essentially, by universal, I mean any Boolean logic can be represented by one of these gates. For a quantum computer, the situation is very similar. In fact, you need single qubit rotations. You don't even need all the single qubit rotations, but I've already showed you effectively we can do all of them very easily. And then we need a 2-qubit operation, and we need just one of them. And this is kind of where the choices very much differ, even for superconducting qubit architecture. Everyone has their favorite 2-qubit operation. At IBM, our native operation is closest to the controlled NOT gate. And what the controlled NOT gate is inverts the state of the target qubit dependent on the state of the control qubit. So saying the control qubit is the first one, the target qubit is the second one. If the control qubit is 0, then applying the C naught does nothing, and the 0, 0 goes to 0, 1. But if the control qubit is 1, then it's going to invert the target bit. And so 1, 0 will flip to 1, 1, and 1, 1 will flip to 1, 0, keeping the control the same. Likewise, you could do, actually, and maybe I can show you a little bit about how entangle comes about. So basically, when you want to build an entangled state, you'll take that control qubit and do something called a Hadamard, which will put it in a superposition of 0 plus 1. So if you're in a superposition of this first state and this third state right here, and you apply the C naught, then that gives you the 0, 0 plus 1, 1 state. And as you can see, it's entangled in the sense that you cannot factor that tensor product. And that's why that state can't be described by individual wave functions. Another thing I'd like to notice real quick is that for the classical computers, there are 2 inputs and 1 output, whereas for all the quantum gates, there's 2 inputs and 2 outputs. And that's because quantum programming is it's unitary, which means it's reversible. The inverse of that matrix is just given by its transpose. So you'll always have, you'll not be able to destroy one of these qubits, except when you do measurement or it decoheres or something like that. But we can also choose other kinds of 2-qubit gates to form a universal quantum computer. So that the controlled phase gate here, we'll just add a -1 or 180-degree phase on this state when both qubits are in 1. And you can also do an I-swap gate that swaps the order of the qubits, and then if something is actually swapped, you get the I, well, I guess it's a 90-degree phase in front of those. It's a square root of -1. So basically, I'm going to focus on the C0, which is generated by these kinds of Pauli expressions I showed you earlier. And this physical technique we use is something called cross resonance, but it boils down to what we're actually trying to get out is a ZX operation. And by ZX operation, I mean we go back to those Pauli matrices, we tensor them together to get a 4x4 matrix, and then we build this unitary out of this exact same expression I was using before, except now we're using a bigger matrix. And if you look carefully at this matrix, you can see that the top left of this block corresponds to the subspace in which the control is a 0 state. And if you look at this one on the bottom right, you'll see that that is the subspace in which the control qubit is, or that is acting on the subspace in which the control qubit is a 1. And if you look at these and compare them to the unitary matrix I showed earlier, you'll see that this is a positive rotation around the x-axis, and this bottom right is a negative x rotation on the x-axis. So what that means is the rotation of the target qubit depends on the state of the control qubit. Kind of similar to a C0, and that's how we build them. We can mathematically say this is locally equivalent to a C0 because we just need to add single qubit gates. So in order to understand how this works in the Bloch sphere, usually as physicists, what we'll do is we'll see how this acts on each of the basis sets. So I just need to know how it acts on 0, and I need to know how it acts on 1. So we assume our quantum computers always start in the 0 state because that's the ground state. It always is kind of where you end up. And we'll represent the initial state by 0, where we have the control qubit in 0 and the target qubit starts in 0, both in the purple vectors. And if we apply the ZX operation to the control qubit, the cross resonance, we will get the target qubit to rotate to the right. So that's what happens when the control qubit's in the 0 state. Now pretend we prepare the control qubit in the 1 state, the target qubit is in blue and it starts in the 0 state. And when the control qubit's in 1 and you apply the cross resonance, the target qubit rotates the other way. So the trick behind entangling things is you prepare the control qubit in a superposition of 0 and 1, which is given by this yellow vector along the x-axis. And then when I apply the cross resonance, I'm simultaneously rotating the target qubit left and right at the same time. And that's a difficult thing to picture, which is why entanglement is a little hard to imagine. So you kind of strain your brain a little bit. Now, physically what happens is why we choose cross resonance is it's an all microwave entangling gate. We don't need any other control knobs such as flux biases or any other lines or magnetic fields or currents or anything else, voltages to do these 2-qubit gates. So it's all in the microwave regime. And what that means is we have less connections to the qubit, which means there's less causes for decoherence, which we'll talk about a little bit later too. So in general, I've got a 2-qubit device right here. And what I'm going to do is, I told you that we were growing the oxide in the fabrication of these. It's just oxidizing aluminum inside of a vacuum chamber. Well, as you can imagine, aluminum oxide is glassy. It's going to be amorphous. And so you're not going to get the same critical current through all those junctions. Critical current technically being the maximum current, the maximum supercurrent you can put through it. But that critical current is directly related to the frequency of the junction. And so in general, we get a nice healthy spread. And in fact, you need a nice healthy spread of frequencies in order for the cross resonance to work, because you'll see that we'll need to identify the qubits by their frequencies. So in general, if you just had 2 qubits and they weren't interacting with each other, you'd have some sort of, we call it energy level diagram. And I think I promise this is as physicsy as it gets. What this is trying to state right here is I have a ground state, 0, 0. And if my control qubit's in the excited state, then that represents the state 0, 1. So that means my control has a transition frequency omega 1, where I'm kind of switching to angular frequency for some reason now. Okay, so forget about that. And I just ask, what if my target qubit is in the excited state? Then I can see that that frequency corresponding to the target qubit is omega 2. And the difference between those two frequencies is this detuning parameter we call capital delta. So typically, this is something you want to be substantial in the order of tens of megahertz or something like that. And so these are things we kind of design and probe for when we're fabricating these devices. So then what I'm going to do is I'm going to couple them together. And I have this microwave transmission. I have this microwave transmission line that's going to come between the two qubits. It's going to couple them, and that coupling is going to be given by a rate J, just typically on the order of 3 megahertz. But what that does is it does a slight hybridization of the control and the target qubit. So the control qubit becomes a little like the target becomes a little like the qubit, and they push each other away in energy to the tune of J squared over delta, where J is the again the coupling about 3 megahertz, the delta is the detuning, say about 50 megahertz. And you can see essentially the wave functions kind of become like each other. And we call this the dispersive regime, where they're not like completely hybridized. They're not like equal parts each other, but they're mostly like, the control is still mostly like the qubit with a small target component of it, and vice versa. And it's this trick in the wave function that allows us to do this, get this dependence, because in the wave functions we have plus or minus J of delta. So what happens normally if you're doing a single qubit rotation is you just apply pulses at a frequency omega 1 to the control, and it has its own kind of input line through a readout resonator that gets in from the outside environment. And same, if you want to do single qubit rotations of the target, you apply pulses at omega 2. Now, what you'd want to do for cross resonance is you want to rotate that part of the control qubit that is like the target qubit. So you apply a pulse that's detuned, and it's actually at the target qubit's frequency, but you apply it to the control qubit, and it starts rotating around that essentially hybridized part of the qubit. And what that means is you're actually driving different oscillations depending on whether your control is in the 0 or 1 state, and that's picking up a sign difference when you're doing the cross resonance. So that's probably as physicsy as it gets, but it's pretty complicated. And this is actually still an area of a lot of research for a lot of reasons, because I'm not telling you a lot of stuff about it as well. For measurements, we are going to take our computer that controls the microwave hardware, and we're going to say do some measurements on Q0 and Q1, which is essentially going to generate some waveforms and mix them together with RF synthesizers. So we do like IQ mixing to build pulses, which for measurement pulses are pretty much just square sine waves. And they're going to go interact with the readout resonator, and that interaction with the readout resonator is going to collapse the qubit into either the 0 or 1 state, and subsequently that pulse is going to be it's going to acquire a phase shift dependent on whether the qubit is measured in a 0 or 1 state. So okay, play it again. There we go. So all these things are going into the fridge. The fridge is a dilution refrigerator that keeps things at 10 millikelvin, and these signals are heavily attenuated to remove any noise from the room temperature electronics and such like that. But the main point is that you have this microwave pulse. It's detuned. It's going to be around 7 gigahertz because it's at the frequency of the readout resonator, and it picks up a phase shift that depends on how you collapse those states. So these are very small signals on the orders of tens of photons. So you've got to really amplify them as they come out of the fridge, and amplify them even more at room temperature, mix them down to an intermediate frequency that could be digitized, kerneled, and classified. So there's even like some areas there that I'll kind of talk about on this next slide. So we have a lot of metrics that go into all the kinds of things I was just talking about, and I basically boiled them down to a few parts. So we have control error. Since our microwave pulses are continuous or analog, our qubits will rotate around, and we'll never get a perfect, say, pi over 2 rotation. We'll always be off by a little bit amount epsilon, which is going to accumulate during the lifetime of a quantum circuit. So that increases error, but it's also a technique we use for calibration. We try to amplify the error as much as we can so that we can make more and more minor corrections onto that amplitude. Another thing we can do, as I said, there are higher order level states, and we just want to stay away from them. Well, it's not exactly that far detuned from the 5 gigahertz. It's at 4.7 gigahertz, say. So if I make my control pulses too short, I'll end up with Fourier content up at that energy level as well. And you'll get what we call leakage outside of the computational space. So at the 2 level, you can excite higher order levels if you try and go too fast. And so maybe now's a good time to say, like, our measurement pulse is on the order of, with leakage, we're probably doing like 20 or 30 nanoseconds. So it's pretty fast, but you can go faster if you're smart about the waveform generation. Our error rates for single qubit control are about 0.1% kind of on average. So we've gotten those to be pretty good. Most of the error comes on the 2-qubit gates, which is about 1% error. And that's because that cross-resonance interaction I showed earlier has a lot more going on. We also have measurement errors where we try to measure these things. And we measure them, we use a microwave engineer's complex plane called the IQ plane for in-phase and quadrature phase. And essentially, we integrate and get these things we call blob plots, where each one of these dots is the result of an experiment. And then we have to classify whether that dot corresponds to a 0, 1, or 2 measurement problem. So kerneling and discrimination is a big part of making the measurement better. And in fact, we can even throw machine learning techniques at that. We can throw any kind of classification. I think we usually use maximum likelihood estimation, but there's a lot of computational techniques you can try and break down. And we have a lot of notebooks online, tutorials that will show you how you can start doing classification of readout of qubits, for example. But a lot of times you'll get decay that's occurring during the process of measurement. And you can see the 2 is kind of decaying into the 1 is kind of decaying into the 0. The 2 doesn't decay into the 0 as much, and that's kind of an important trick that we started using. And then moving on, we have crosstalk. So I talked about we have this coupling J, which is mediated by a microwave resonator. Well, that microwave resonator is always there. It's not tunable in our standard case. We have research projects for tunable elements. So basically what that means is every qubit is feeling the effect of all the qubits it's attached to while you're doing that. And so one of these experiments is what it's doing is it's considering the cross-resonance gate, whether or not that qubit is in the spectator or neighboring qubit is in the 0 or 1 state. And we see that the excited state of that in the 1 state can shift the frequency of the state we're trying to operate on by like 1 megahertz in this example, which is quite a bit. That 1 megahertz, this detuning in our qubits, that will cause unintentional Z rotations around the Bloch sphere effectively. And that will lead to errors as well. So actually, this is one of the reasons, and I'm not going to it through this talk, but you might have wondered why we're using this hexagonal lattice at IBM to build our quantum computers out of. And the reason is this: we actually found we can increase the overall device metrics if we were to limit the connectivity of the system into something a little bit smaller but can still support a quantum error correction code. And then we have the more kind of quantum-like problems, which we call relaxation. So we have these things T1 and T2. T1 corresponds to relaxation from the 1 state to the 0 state. So I prepare my qubit in the 1 state. It will spontaneously emit to the environment. That's going to have a lot to do with the environment itself. Effectively, it's going to be bound by an LC time constant, just like for a circuit. We have an equivalent thing we call the Purcell effect that corresponds to that. The qubits can also couple to defects. We usually call those two-level systems, or any other channel where it can emit to the environment. That's going to cause, any coupling will cause a spontaneous emission. There's other crazier phenomena such as quasi-particles and vortices that are inherent to superconducting, a phenomenon that can cause it as well. We also have this thing called decoherence, which is a combination of this pure dephasing, which is a purely quantum mechanical thing. What this is you prepare your qubit in a 0 plus 1 state, and you're going to get some phase difference that oscillates around that state. So the relative phase between the 0 and 1 will cause these longitudinal errors on the qubits. And the combination of that and the relaxation gives you this overall decoherence T2. So these fluctuations, this dephasing, is typically caused by fluctuations in the energy levels. Like I mentioned, that can cause problems. That can be caused by thermal broadening, meaning your qubits are too hot. So there's a broadening of their levels. There could be magnetic noise if you had tunable qubits, because you could have a flux you could have flux noise that arises from current noise, or actually any other kind of even molecular or atomic defects that absorb on your qubit when you're cold. So there's a number of things that can happen. Anytime you're measuring, you're collapsing the quantum state, so you're dephasing it. But that also means if you have noise going down at the measurement frequency, you're also dephasing it. And then it's ultimately limited by relaxation. So kind of the idea is we want to focus on algorithms that can tolerate moderate errors while we improve the error rates. So we have certain classes of algorithms, typically like variational type algorithms that are hybrid classical quantum. And then in the long term, we want to improve the error rate so that we can implement error correction, which we're still a little bit away from. We're kind of at the threshold of where it makes sense to start building logical qubits that are at least more immune to error. So since we're in this area of noisy systems, we decided it would be good to come up with a metric to try and take all these things into consideration. And to that end, IBM's come up with something called quantum volume, where it doesn't take just into account the number of qubits. Now, the number of qubits, theoretically, if they were perfect, would give you this exponentially large Hilbert space in which to perform computation. So that's what a lot of people talk about. But it turns out the errors are actually, kind of more severe. It's a lot easier to build a lot of qubits that are pretty noisy than it is to build fewer qubits with less noise. Well, we're trying to build them both in the same way. The connectivity, more is generally better from a quantum volume perspective, but we find it's worse because of a spectator error perspective. And then the gate set, or the kinds of different operations you can do, that can increase things. And that's maybe not so much for superconducting qubits, but other modalities might have that. So this was a type of benchmarking that we kind of tried to tailor to the LINPACK benchmarking that HPC is using. But we're, instead of like how fast of a linear algebra problem, we're doing kind of how reliable can we do an arbitrary linear algebra problem. And so what I mean by that is every operation between two qubits is represented by a random SU4 matrix, like I was saying before. And then we kind of make this an arbitrarily large matrix by doing permutations given by these pi's here. So what those pi's and those u's effectively mean is I'm going to do arbitrary operations between all of my circuits. I'm going to repeat them for a number of steps, which we call the depth. And we're going to do this on a number of qubits. So we have a unit of depth is a permutation and a U4 between neighbors, which is effectively a U4 between any random ones. And then we're going to see what size of square circuit we can actually do, and that will be the log of the quantum volume. So it's essentially, like LINPACK, the most representative of short depth general purpose quantum computations we can have. For these, we're just looking at qubits. We're not looking at higher order levels. I think we're allowed to look at Ancilla. Yeah, Ancilla are good. You can use those, but not the higher energy levels of the transmons. And we and a number of the ion trap quantum computers have been using this as their metric. And one of the things that ion traps have is they have a not just the ground or excited state of the ions, but they also have emotional degree of freedom because they're laser cooled down to the ground state motion. So they can use this as an additional quantum bus, which allows them to do some kinds of things that superconducting qubits can't do. So that's kind of like overall, the metric is how large of a square circuit can we do to within accurate enough, which means to like 2/3 reliability with 97.5% of statistical certainty. So let's just see what that looks like when you're mapping these to problems, because I think this is where a lot of the we call them transpilation problems arise. So I'm going to go back to Tenerife, which is a 5-qubit device. And I'm going to say, well, if I want to go up in quantum volume, so essentially what I'm going to do is I'm going to look at this. I'm going to try and do a 3-qubit depth 3 circuit, and then a 4-qubit depth 4 circuit, 5-qubit depth 5 circuit. So if we look at this 5-qubit device and I say I want to do a depth 3 circuit, well, that's not bad, because in this configuration, I can pick either two sets, this 0, 1, and 2, or this 2, 3, and 4, and those form a fully connected 3-qubit pair, which means I don't need to swap any quantum information around, which is pretty expensive. So what happens is the length or the depth of that will correspond to, on average, the number of C0s will correspond to 3 times the depth. And since that's the largest part of the error, that's really what you want to keep your eye on. However, if you want to look at a 4-qubit subset of the same, you'll look at this topology and notice that there's no way I have any 4 connected qubits on this device, which means I need to introduce swaps, and swaps take up 3 C0s. There's some clever compilation techniques we can use to try and reduce that, but in average, it's 8 times the depth of the circuit, which means it's very, very expensive the further you go in depth. So for example, if we just went to a depth of 1 on this 4-qubit, on this 4-qubit attempt, we're just trying to do depth 1, we can reasonably get the quantum volume. And the way this is actually calculated is we take all the bit strings that are possible from the random outputs. They're each corresponding to a probability that we can calculate with a classical computer using just a unitary simulation of this. And then what we're going to do is we're going to throw away all the results that are less than the median, which is represented by this dotted line. And we call the ones that are above the dotted line the heavy outputs. And so the heavy outputs are wherever your quantum computer agrees with your heavy output from your classical simulator, and then you just add them up together and you get a heavy output of 0.79. That's greater than 2/3. That means that is a success, that's not a full quantum volume calculation. If you did go to the full quantum volume calculation, you'll see you have about 32 C naughts. You really wipe out the ability of the quantum computer to replicate the the classical outputs. So in this case, you get a heavy output of 0.51, given by where they agree, the sum of where they agree, and that's less than 2/3, so that's considered a failure. So this is basically how, this is our kind of overall benchmarking that we're trying to do, and we're trying to think about for quantum computers in general. This works for any gate-based quantum computing model, I should say, as well. Okay, so what do we do when we're thinking about how do we take this abstract quantum circuit and map it to an actual quantum circuit that runs on a device? We go through this process called translation, and this is actually kind of where I've started to do some work where I'm thinking more like a computer scientist in my day-to-day goings-ons. So you do these rewriting steps where essentially I'm not really sure what a virtual circuit optimization is, but you essentially take away any 3-qubit gates because we don't have those. So we need to compile those down to 2-qubit gates. We need to place them physically on an architecture that is a physical system that does not have all the has much more limited connectivity than this arbitrary abstract quantum circuit. You want to translate all the operations you're doing into the native basis gate sets. So for us now, we're using the square root of an X operation, which is a 90-degree rotation on the X-axis, and arbitrary Z rotations. As our single qubits plus a C naught, even though I'll show you later, C naught is really, that's not physically the native gate. That's just kind of what we give you and what you will transpile to, but we're trying to improve that as well. Then you can look at the error rates on these circuits. So not all we try and make the device as good as possible, but you're going to have some variances in the coherence times in the 2-qubit gates on these systems. So you can perform further optimizations and try to figure out how to best map a circuit. So I wanted to say is like one of the things is you have a swap, for example. That swap is equivalent to 3 C naughts, this quantum circuit down here. So this, when you map it to our native gate set, it's a very expensive circuit because each one of those is 1%. And then this native gate set here, we're going to take things like Hadamards and X gates that you might know. And this is actually a little old, this is our former native basis gate set where we use these single qubit rotations defined by unitary angles. But yeah, I guess I should update that slide. But I'll give you another flavor of that later, or I'll give you a flavor here, then another flavor later. So we have this circuit, which is like a Bernstein-Vazirani circuit that you'll see a lot in your algorithms studying quantum computing. And we want to map it to our 5-qubit device here. Well, essentially we need to transpile it, and just to see, like, if you thought about making a good mapper and you realize that this Q4 has a C naught between all the other C naughts, then you want to remap that that Q4 to Q2 here, because that Q2 is attached to all the other qubits. However, if you just blindly mapped all the numbered qubits to the same thing, then you'd have C naughts all with Q4, which means you need to swap the data in Q0 and Q1 through Q2 or something because they're not connected to each other. So you end up getting a lot more C naughts, and when you run it on the actual hardware, you get the correct answer most of the time if you had a good mapper, but you get a result that's indistinguishable from noise if you don't use a good mapper. So I just wanted to kind of give, and I realize we're a little low on time, so we'll just kind of go through KissKid Pulse relatively quickly, and I'll show you how we used a different compilation technique to be able to perform a quantum simulation that was impossible otherwise using those C naughts. So KissKid is our open source framework for quantum computing. Generally, it's an IBM product, but it's an open source, open to anyone. It's under Apache 2.0 license. It's mainly written in Python. You can access our devices with it. You can access other people's devices. You can access simulators. You can access whatever. It's essentially made out of three elements, where Terra is kind of the bedrock of the elements, which allows us to build, run, and compile, transpile, and run circuits on actual hardware. We have Ignis, which are tools for characterizing and mitigating error. So these other techniques like quantum volume or randomized benchmarking to determine gate errors are within this library. Air is basically simulators, and those are helpful for algorithm research. And then Aqua is pretty much our very high level, which is basically meant for domain level experts to do run applications in AI, chemistry, finance, or optimization without really having to know much about quantum computing. We have community. We're on Slack, GitHub. I think we're on Stack Exchange as well. You can pip install us. And what I want to tell you is a little subset of Terra we call Pulse. And basically, this is motivated by these control improvements that we had, where we actually went from quantum volume to 32 using just these quantum volume 32 to 64 just using these improvements, and we're up to 128 now using similar improvements. And it was all done in control. It wasn't no improvements in hardware where you usually think like, oh, I need to make my qubits cleaner. I need to make their microwave environment cleaner. This was none of that. This was done on the same kind of system. What we did instead is we have these like decompositions, like linear algebra decompositions that you might test in LinPack. We do things like CAC decompositions, which allow us to break down any arbitrary SU4 into one of these circuits with three C naughts and a few single qubits. So what we actually did here was something that was locally inefficient. We took all the single qubit gates and tried to move them to the left or right of that circuit, if we could, essentially through the entanglers, which would in general make a less efficient circuit on its own. However, when you start combining these blocks of SU4s with each other, you could compile down those single qubit gates in such a way that you would get a lot lower overall single qubit gate per circuit. I'm sorry, per depth unit. And I believe that went from 9.3 singles to 7.4 after this compiler trick. So it's a locally inefficient compilation technique, but overall it gives us better quantum volume. There are other pulse level techniques we use that say involve the qubits, such as dynamical decoupling, where we kind of keep the qubits busy by flipping them around one way and then back the other way. And that kind of has an effect of suppressing the errors that build up either from low frequency noise or other unitary errors. We did another trick where we did excited state promoted readout, where at the very end of the circuit, we tried to promote the qubit from the 1 state to the 2 state. Now that can only occur if it's already in the 1 state, because otherwise there's nowhere for it to go, because these are different energy levels. And we measured the 2 state, and that gives us greater distinguishability in the IQ plane, which I think is still being worked on with some machine learning techniques. And the other thing is it suppresses the relaxation that can occur, because the 2 state does not like to decay into the 0 state. It will usually decay into the 1 state and then from the 1 to the 0 state. So that physically that excitation suppressed, so we get a benefit there. Then also we made shorter 2 qubit gates where we got rid of this echo that is used to eliminate some undesirable unitary terms, which I'm kind of glossing over, in order to get a direct C naught, which is, it was not as good, but it was more efficient. And overall it gave us a, it let us run our quantum volume in less time, which overall was the thing that mattered. So these 4 combined, and no subset of them were needed to go increase the quantum volume. So pulse is one of those things that allows you to do that. And basically the idea is each one of these abstract quantum gates needs to be mapped onto a actual pulse schedule that's played out on a quantum computer. And we introduced this, I guess, 2019, and we have publicly available devices where you can play with these microwave pulses. And basically we're doing this is because there's a lot of ways you can improve your hardware. There's hardware solutions such as making things better, but there's also control solutions such as calibrating better or pulse shaping the right way, or you can even use, people do optimal control in AI to generate pulse shapes. That's another thing people do these days. And without going into the details, I'm just going to say that there's always a control solution. We basically have a number of different channels. We're typically controlling the qubits as a drive channel, which is typically an on-resonant drive used for resonant single qubit interactions, and a control channel, which is typically an off-resonant cross-resonance interaction, in which we can play pulses or delays. We have measurement channels for measuring and acquire channels for acquiring the result of that measurement. So typically we're playing pulses and we're playing out pulses and putting delays between those pulses, but we're also doing frame changes, which are these virtual Z rotations. And at the end of the measurement, we're acquiring it. Or actually, we have, that's not exactly true because we have mid-circuit measurement capabilities now. So basically we're forming these waveforms, which are specified by an array of complex numbers, basically specified by the carrier signal's frequency and the phase of that frequency and the amplitude of that. So this allows us to kind of insert these signals into the circuit diagram level of what a quantum computer looks like. This is the kind of thing I look at and think about when I put together things in the fridge. Like if I was in the lab, this would be the kind of circuit diagram we'd be looking at. And it just shows you how these waveform generators are mixed together with RF synthesizers to form the pulses, and how they're blocked off with other elements such as microwave switches, and how things are then kerneled and discriminated. So if you pull this apart, you can see there's a lot going on under the hood in this basic operation. And I should say the Hadamard there, that puts the Q0 in a superposition of 0 and 1. And then the C naught generates that entangled 0, 0 plus 1, 1 state, which is kind of our favorite building block of things. So these frame changes are just Z rotations. They're done in software, so they take up 0 time, so they're perfect. We also have drag, which is something we do to try to prevent the higher order levels of the transmon from interfering with our control. We have echoes, which eliminate those extra terms that come along for the ride in the cross-resonance Hamiltonian. And we have rotary echoes, which further prevent more of those extra unitaries from coming around. So these are all kind of control things that we use to suppress undesired interactions to get out the best ZX we can, so we can build these C naughts over here on the left. And then I basically, in the last few minutes, just want to breeze through some recent work I did, which involves some of these techniques. And this came about from the other way of Richard Feynman wanting to have a quantum computer, a computer that obeyed quantum mechanics so that he could solve his molecular problems, his nuclear problems and stuff, because those problems blow up each time you add a electron or orbital, for example. So basically, the idea is you have this quantum system, and you know that it maps under some sort of evolution of a unitary from time 0 to time t. Well, what you can do is you can figure out a way to map that system onto a quantum simulator. And so you map that onto a state psi at time 0. You evolve under some different unitary that's been mapped there, and you get to a point psi of t, at which point you can perform a measurement and map the results of that measurement back to the quantum simulation. And these are essentially done with these things called Hamiltonians. You might have heard that before in studying quantum computing. Hamiltonians is how physicists love to describe systems, because essentially they describe the time evolution of the systems. It has to do with the energy of the systems, which determines the time evolution. And so roughly you would understand your system as a system Hamiltonian that you're trying to simulate, and a simulated Hamiltonian that kind of explains that to you. And for example, we do this a lot with chemistry. For example, if we want to understand how electrons in a molecule work, they're described by a Hamiltonian that has these, call them fermionic creation and annihilation operators. You don't need to know what that is other than they obey the statistics of fermions, whereas qubits don't obey the statistics of fermions. So if we want to map them onto the qubits or spin Hamiltonians, we have to do one of these decomposition or transformation processes, such as Jordan-Wigner, which will then give us a Hamiltonian that we can understand on our quantum simulator, for example. And that actually, this is where what I'm going to talk about branches with algorithms like variational quantum eigensolver that was used in this work by Abhinav Kandala to calculate the ground state energy of molecules. So I was looking more into doing actually Hamiltonian evolution directly on the system. And so what you would do is you would take those terms, those little sigmas on here corresponds to the Pauli matrices. Sorry for writing everything in different ways, but we always do that. So these sigmas here are just the Pauli X, Y, and Z matrix. So this is just two Z Paulis tensor next to each other, but it's been exponentiated because those were terms in the Hamiltonian. Well, I can describe that evolution with this circuit right here, a C naught and RZ of an amount theta, and it's another C naught. And then you can build a library essentially by applying identities with other basis elements, so you can form any interaction you want. So once you have your Hamiltonian mapped to your simulated system, which is the quantum computer, you can build those Paulis, or you break them down into 2-qubit terms and then build up those Paulis. So here's like an XY, actually YX, we always change the way we go in order. And it turns out you can build up multi-terms, whatever. It's really easy algorithmically to just build a circuit that does this interaction. And this is very nice because you have your Hamiltonian, which is now in these terms, and you have kind of a formulaic circuit operation that you can build. So then what we'll typically do is these terms do not commute with each other, which means, A times B minus B times A is not equal to 0. And that's true with these Pauli terms. So you want to break down that, you break these things down so that the non-commuting terms don't not commute so much. But we're not going to get into that so much here. The basic thing is that if you wanted to take this Hamiltonian we were trying to do a simulation of, I don't think I have too much time to go into that, and I'm just going to write it down for you. We can write this as a quantum circuit just according to that kind of mapping I was showing you before. This would kind of be like a textbook simulation circuit. So basically, for each one of my qubits, I'm doing a Z rotation, and then I'm doing YX rotations, and then this combined YZX rotation. And we ran this on IBM Athens, and it turns out it doesn't work because for each one of these C naughts, you have a 1% error. For these controlled Zs, they also have C naughts, which is a 1% error, plus a couple single qubit gates. And these qubits were not attached to each other, but this term, the Hamiltonian, mandated it, so you'd have to do a swap in order to do that C naught operation between Q0 and Q2. So this ended up being very expensive, and you were not doing a very big rotation around the YX axis. These rotations for our simulation were typically pi to the 10 to pi of the 3. So that's a very small angle of rotation for these entanglers, where each one of these C naughts gives you a pi over 2 of entanglement, essentially. And 2 C naughts will give you a full pi of entanglement. So we're really kind of overkill on how much entanglement we're using versus how much we're needing. And this amount we're using here that's determined on how much we break up the steps. And so I think we broke it up into 4 steps for a second order Suzuki Trotter decomposition. But that's not really what I wanted to show you. I kind of wanted to show you that, well, if we know what the pulses are doing, then we can modify those pulses and get a scaled circuit that's different from this digital circuit. So what I'm going to do is I know what my C naught looks like because I'm a pulse user and I know what my native basis gate sets are, and they're composed of these things. But instead of getting that full pi/2 of entanglement, what I can do is start scaling and stretching them in a way that I know should work, being an experimental physicist, I guess. And so you get this kind of basic atomic interaction of entanglement, and you scale that in such a way that you generate the same interaction but with less pulses. And so this is what we were able to get. This was a YX interaction. It's just one of these ZXs with a couple different single qubit rotations on the beginning and end. And so that's equivalent to this digital YX interaction. And what happens is we can benchmark these using a process called quantum process tomography. And we monitor the fidelity of those circuits. And what we can see is for the digital ones, well, we're only having a single qubit gate here. We're always having 2 C naughts in a single qubit gate that probably doesn't really depend too much on this angle. And so our process fidelity is pretty similar. So all the blue dots are kind of in a line. And the other thing is if we actually scale our circuits and shrink the amount of entanglement going on as we need it, and we benchmark something equivalent, we can plot that as a function of theta and see that we get much better performance for small angles because we're not doing as much entanglement. And then by the time we get to the full pi amount of entanglement corresponding to the top digital circuit, you get the same thing. And you can just look at the bottom plot, which is the relative error reduction in that. So this kind of naively confirms what you would expect to happen, because that's where most of the error is. If you shrink it down, then you get less error, and that's more or less a linear relationship. And what's even better is we were able to do this analytically. We didn't need to recalibrate anything. So we could just do this, do this by scaling the pulses in a smart way without even recalculating or we would recalculate the pulses, but not recalibrate anything. So that didn't require sending any extra jobs over the cloud and putting them in a queue and then waiting for all these things to happen. So just to build the schedule of pulses that in one of these steps, in one of the steps of what we were trying to do, to give you a idea, the left is the scale technique where we see the cross resonance are in the yellow pulse and the yellow pulse shapes, and same on the right, but that's the digital implementation. So you can already see that the schedule is 60% of the length using the scaled circuit than the full circuit, which means you're definitely not getting hit by coherence, or you're getting hit by qubit decoherence 60% less, but you're also doing these operations which are not limited by the coherence, and you're doing a lot less of them, which kind of have the most error of the circuit. So knowing this, we were able to, actually just added this to KissKid last month, do a process called template optimization, which is another computer science process we put out through our Zurich research lab, a technique called template matching in order to find patterns in quantum circuits. And now we have it implemented, and I'm kind of testing it out, doing certain things that will allow you to break down these interactions in a smart way so that you can generate these pulses on, as a circuit, like just as we did, without further optimization or control, because we're essentially can offer you the ability to do quantum simulation more efficiently. And so that's the kind of computer science result of this experiment. We also have a lot of other things going on. So I want to say mine's the only thing, that's just the thing I'm most familiar with. But we've introduced a mid-circuit measurement and reset. That will allow us to do a lot more with less quantum resources, such as ancillas. For a lot of algorithms, you'll need less resources because you have the ability to operate and measure qubits, and eventually we'll have the ability to dynamically do conditional statements on those qubits, and that will be coming later this year. So it's going to really open up the possibilities of algorithms on quantum computers. And we do other kinds of ways to mitigate errors by understanding what the errors are things such as measurement mitigation, where we can measure a preparation of all our qubits in different states. And because that's a classical process, we can just kind of invert the matrix for that process and apply it to our result to get a better readout, essentially. So I just kind of wanted to, I went through a lot of different things I think you would all be interested in, and try and give you a flavor of these maybe lower level type quantum operations that are just as important for squeezing out as much performance out of near-term quantum computers. So I thank you very much for your time.